Hello and good afternoon, and welcome to the last GReTA seminar this year, so our Christmas edition, if you like. I'm trying to grow an appropriate beard for the occasion, as you can see, and I tried to find a jolly hat, but I couldn't find one, so you have to do with what you can see at the moment. So yeah, it's my pleasure to welcome Steffen again. I think he's gave a presentation in this seminar before, and obviously he's been sort of participating in a lot of the seminars, so you will all know him. But just briefly, he is in King's College in London, working there in the computer science department, and he's also leading MDEnet, a network, EPSRC network on model-driven engineering in the UK. Apart from sort of doing sort of work on graph transformation and model transformation more generally, of course. Yeah, and today he's going to talk about activation diagrams, as you can see, which is something that I hadn't heard about before. So I'm looking forward to learning what those are. Please, Steffen.
Okay. Well, thank you, Raiko, for the introduction, and thank you indeed for inviting me to present on this. This is work that we did together with Javier Martinez, Daniel Struber, Mikael Hokas, and Alexandra Bordsell. And some of the work I'm going to talk about is also work that is jointly with Jens Koziol and Gabi Henser. So what I'm trying to do in this talk, I guess, is bring together a couple of pieces of work that we've been doing over the last 3-4 years or something, and sort of linking them together a little bit. The activation diagram stuff was, I think, published this year at TSE, and I think Javi gave sort of a general first presentation about it as SPLC as well. But then there's also something around consistency sustaining and consistency improving GT rules here in this presentation today, which is to sort of work with Jens and Gabi and Daniel in that case as well. So it's about activation diagrams for generating consistency sustaining GT rules, and I'm going to try and do some slightly more general context setting and explanation, but then a lot of the talk will focus on a particular example where we actually spelled this out in some amount of detail in the context of product line configuration, with where there now is also a tool called Acapulco. So let's get started into this. And I want to start with this idea of consistency as a graduated property. So when I talk about consistency here, what I mean is if we have a graph and we have a set of constraints, a set of graph constraints, then we can say this graph is consistent in relation to these constraints if all of the constraints are satisfied in that by that graph. And typically what people have done in the literature in terms of sort of the formal framework that people have worked with is you could either say a graph is consistent with regards to a set of constraints, or the graph is inconsistent with the set of constraints. But actually, in the context of work that we were doing in the context of sort of search-based optimization and generating good operators for that, we realized that that's actually not enough, that's too coarse granular as a notion. And that, in fact, intuitively, quite a number of subfields already were using a more fine granular notion. It just nobody had really spelt that out formally and really tried to understand what it means formally. And that's a notion where we treat consistency as a more graduated property. So where we're not just talking about a graph being either consistent or inconsistent, but where we have sort of shades of gray in between, right? And where we can sort of say, where we can basically compare two graphs and say one is somehow more consistent than the other. And the way we do this is that in particular for graph constraints that start with a for all quantification. Existential graph constraints are a little bit boring because they are essentially 0 or 1, right? But for all constraints are interesting because they're basically, there could be multiple places within the graph where that first part of the graph constraint matches. And in each of those locations, a constraint might be satisfied or it might be violated at that location. And so it becomes relevant to ask, if we look at all of the possible locations where we might check this particular constraint, what percentage of those are satisfying the constraint and what percentage of those are violating the constraint? And that gives us a measure of how consistent, if you will, a graph is with a set of constraints. And if we think about this, then it becomes suddenly, as a next step, quite relevant to think about graph transformations and, as a next step, graph transformation rules as having sort of different sort of characteristics, different properties. So they can be constraint preserving, and that was a apologies, that was a notion that already existed, which was basically say, if a constraint isn't violated in a graph and we apply a rule and we apply a transformation to it, then the constraint is still not violated. But they can also be what we call consistency sustaining, which is to say they don't change the number of constraint violations. Sorry, they don't increase the number of constraint violations in the graph. Okay, so if we apply a transformation or we apply the rule and more generally, then the number of constraint violations in that graph doesn't change. It doesn't increase. Sorry, I keep getting this wrong when I don't watch out carefully. A slightly better property is what we call consistency improving, which is to say, not only does the number of constraint violations not increase, in fact, it decreases. So the rule or the transformation, or rather, actively fixes violations. But there may be other violations that might remain, but it actively fixes at least one violation. And then, of course, we have constraint guarantee, which again already existed in the previous literature, which sort of takes this binary approach, which is to basically say, whatever the graph looked like before, however badly it violated some constraint, if we apply this transformation or the rule, it will be afterwards, it will be completely consistent. Okay. And it turns out that these sort of notions are actually quite nicely related to each other, as you can see in these sort of implication diagrams, right? So if we have a constraint guaranteeing rule, every constraint guaranteeing rule is also a consistency sustaining rule, or in fact, there's also this notion of directly consistency sustaining, because it's easy to see that you can be consistency sustaining by breaking a constraint somewhere while fixing a constraint somewhere else, right? You might still then end up with a non-increasing number of violations, and that's a directly consistency sustaining rule must not do that, essentially. And then all of these kinds of rules are all constraint preserving rules, but also on the right side for improving rules, there's a similar sort of relationship in that essentially every improving rule is also a consistency sustaining rule, and then fits into the left diagram as well. Right? The details are in the paper that I've listed below, which is sort of the journal extension of an ICGT paper from, I want to say 2020, but I might be wrong, might have been 21 in fact. So this is nice. This gives us a way of looking at rules or transformations and saying, how do they affect the consistency of a graph incrementally? And in fact, it turns out that we can check the consistency properties of rules statically to some degree, right? There's a bit of a window there, because what we can do is we can give sufficient criteria, but we can't give completely necessary criteria. And this is just a copy of the table here. I don't want to go into the details of this in this talk, but essentially what we can do is by creating this check rule here, which is essentially an identity rule, we can then use dependency analysis, standard dependency analysis, between the rule that we're actually interested in and a particular type of check rule to understand whether the rule is consistency sustaining or is consistency improved or potentially consistency improved. So as you can see, we can check whether the rule is definitely not consistency improving, and we can check whether it's consistency sustaining, but then it's sort of a half decidability kind of thing, right? And it depends a little on the structure of the constraint. And basically, as you see, as you add more nesting levels, well, you've got to do more checks because you've kind of got to walk through the levels. This is the sort of constraint, perhaps, that we talked about initially, right? Where we say exists C1 and then something here. Then what we want to make sure is basically the graduated consistency property is if we were where we can match C1 in our graph, this second half may or may not hold, right? And so that gives us the number of potential violations. And then here we look at how we can check whether a particular given rule is consistency sustaining or potentially consistency improving. So this is nice. It allows us to, if we manage to handcraft a rule, we now have a way of checking whether that's a good rule, if you will, or not. But the other way around, of course, is also interesting, right? It's the question of, so how do we produce these kind of rules? Because they're potentially quite difficult to create, right? So how do we generate these kind of rules? Now, there's an easy thing that we can always do, right? We can always go and say, well, my rule's going to do something, it's going to make some changes. I can try and work out under what conditions those changes might cause a constraint or create a new constraint violation. And then I'm going to write a knack for my rule to say, in those conditions, please don't use the rule. And that has a good chance of making the rule consistency sustaining. It doesn't necessarily tell us anything about consistency improving, but at least it makes it consistency sustaining. But of course, it also has a really good chance of making the rule essentially non-applicable in most interesting scenarios. So a more interesting way of doing this is by saying, well, let's split our rule, if you will, into an edit operation and a repair operation. And that's some of the work that I've done with Alex in particular. He's been doing quite a lot of work around generating these kind of operators with regard to constraints that are about multiplicity. But he's done this a lot of time. He's done this by basically really understanding how multiplicity patterns work and then defining particular patterns, manually defining patterns of generating results. But one of the things that he came up with was this categorization here, this split of how do we think of the different parts of such a rule, right? So there's an edit operation. That's the thing that we're actually interested in. The rule makes some change to the graph that we're interested in, which can be an atomic change, and in his case, typically was an atomic change. So it creates or deletes a node, or it creates, deletes, or rewires an edge. But it could potentially also be a more complex change, right? A compound change that does multiple things. But then, in order to ensure that the rule is consistency sustaining, we need to have some extra stuff in our rule that repairs any damage that might have been caused. And again, that might be atomic. One way of doing an atomic fix is by doing nothing to repair, but instead just making sure we never apply the rule if it could break something. But it could also, there are other atomic fixes that you can do, for example, for multiplicity. It's about things like going, okay, well, if I've removed the edge from this node over here, but there's a minimum multiplicity for that node to be connected to other things, I may have to find something else that it can now be connected to. So I may need to rewire another edge. And iterative means I may have to do this for multiple things, right? But it's the same node maybe has edges to many other types of nodes that it has multiplicity constraints for. So I have to do a fix for that and for that and for that. Recursive is more interesting. Recursive is when my initial repair operation, again, creates an edit to the graph that might violate a constraint itself. And so I now need to also repair that violation. And that, of course, very quickly becomes really painful, right? So, but that's the bit that we're going to look at in a moment with this notion of activation diagrams, is how can we try and get a handle on these recursive repairs in the rule generation process. And the reason I hope why this becomes painful really quickly is because, of course, it has the potential of exploding exponentially quite quickly, right? Because every change you make to the graph could potentially, again, violate something that requires a repair, which itself might violate constraints which require a repair, which and before you know it, that sort of network has branched out quite hugely. Okay. So let's look at a specific example of such kinds of rules and such kind of repair generation. And we're going to look at an example that might not immediately strike you as a graph transformation problem. The optimal configuration of software product lines. Let me perhaps first introduce the example a little bit, and then I'm going to sort of mention a little bit why we approach this from a graph transformation perspective, and what it's taught us that we're now trying to sort of generalize a little bit from that. So here is the problem description, right? So in the world of software product line engineering, we're thinking about software systems where we've basically sort of got families of software systems that are all similar in some ways, but have variations among them. And one way of capturing these variations is using a feature model. And I've got an example here that I've stolen from this publication down here, where we've got a feature model that basically shows us what the variability is. So this tells us for this smart home application, we have to talk about elimination options. We may want to talk about media options. We may want to talk about security options. And if we're talking about elimination options, then we have to choose between manual or automatic. And we cannot choose both. We've got to choose one or the other. So that's what this XOR combination here says. And if we're choosing the media option, then we get to choose between camera, audio, and cell phone. And we can choose one or multiple ones of those. We've got to choose at least one. But we could choose multiple ones of those. And then, similarly down here, it goes further down. Oh, and then there's some other additional things here that say, well, if we've chosen the sensor feature or we've chosen the detection feature, then we have to also choose the alarm feature. Or if we've chosen the blinking lights feature, wherever that sits here, then we have to choose automatic and we can't have manual illumination. Kind of makes sense, right? So if there's something special about how the lights behave, it probably needs the automatic controls. Okay. What this thing also does here, this example quite nicely, it shows us that these features might come at a cost, or they might have effects on system performance or security or all kinds of other non-functional properties. Okay, so in principle, we can attach with these features to these features information about costs, etc. And then we might have an overall sort of constraint or an objective or a set of objectives that we want to achieve. And the way we work with this is that we construct these so-called configurations. You can see an example over here, and so you see sort of everywhere where it's green, it sort of says that feature has been selected. And there are tools out there. I think this is a tool called Feature IDE here that allow you to run these configurations and automatically consider the constraints that are imposed by this feature model, right? So it's important to note that the feature model defines constraints over the configuration, right? And we can think of the configuration as a simple graph that has nodes that are enabled or disabled or present or absent, however you want to model that, and that are sort of linked to these feature nodes in the feature diagram. Okay. So I've already said feature models induce these constraints over configurations, and here you kind of see the typical constraints that you have, right? So if we have a feature F that's activated, so that's in our configuration, and it has a so-called mandatory child, then that child also needs to be activated and needs to be selected in the configuration. Similarly, if a feature is in the configuration, then its parent features with a feature above it in the feature diagram also needs to be in the configuration, and so on, right? So there's these 7 constraints that people typically associate with feature diagrams, one of which somewhere is if there is a requires relationship between 2 features, so one of these cross tree constraints, then obviously if one is selected, then the other one also needs to be selected, and so on. Now, if we've got non-functional quality properties attached to these features, and we can build configurations, well, one thing that's easy to see, I think, is that for a given feature model, you don't have to build a particularly big feature model for the potential configuration space to become really, really large quite quickly. But then an interesting question is not just, I want to find a configuration, but I want to find the optimal configuration given the associated quality values and quality attributes that are attached to the various features. And if we've got this huge space of potential configurations, that obviously becomes a really complicated problem really quickly. Even more so, typically we don't just have one objective that we're interested in, but we tend to want to balance across multiple objectives, which can be contradictory, right? So we might be interested in the best possible performance that uses the least amount of battery, and is the most secure configuration as well. And you know, one of those 3 will have to give, essentially. And so it becomes a multi-objective optimization problem to find these optimal configurations. And what people typically have done so far is they've used search-based solutions. They've come out as working the best. There've been some other attempts as well, but search-based evolutionary algorithms have typically come out as delivering the best results here in finding these optimal or near optimal configurations, and typically using the genetic encoding and this IBEA algorithm here. And what they do is they typically encode the feature selection into a binary string like this, right? So basically you do a traversal of this feature model tree, and that gives you a sequential arrangement of the features. And then for each feature, you have a bit in this bit vector, and if it's 1, then that means that feature is currently activated, and if it's 0, then that means that feature is currently deactivated. And once you have that, you can throw standard genetic mutation and crossover operators on this. So your standard genetic mutation operator becomes a bit flip in this vector, and your standard crossover becomes, you know, let me cut this vector at some point and then swap parts between two vectors. And that's nice because it runs nicely and efficiently, and you don't have to invent new search techniques. You can just use standard search techniques. But it has a big problem in that this encoding is in no way whatsoever locality preserving. And that means pretty much any mutation or any crossover will break some of the constraints that the feature model has induced. And that's a bad thing. Typically for search, if your search regularly produces invalid candidate solutions, that will slow your search down, and it will often make it so that your search doesn't find the interesting solutions or the best solutions. What the typical approaches in the literature do is they then introduce these sort of repair operators, which basically tends to be, let me throw a stat solver at this that kind of fixes the broken bits and creates additional selections in this feature vector, so that it's indeed again a valid solution. And of course that's costly. But it also means it doesn't that repair step doesn't know how we got to this point, and so it might also just remove changes that we've just done, right? And so we try to explore in a particular direction, and then we do the repair, and that essentially takes us back to where we started from. And that, of course, isn't particularly helpful in trying to find good solutions. And also, the search typically will keep some of those broken solutions around in the population for a while, which means that we're effectively only searching with part of our population because we've got all of these things that are currently broken. They might get repaired at some future step, but at the moment they're broken. And in fact, with these search tools, sometimes you can get to the point where you stop your search after a few hundred or 1,000 or whatever iterations, and none of the solutions in your population are currently valid. And that, of course, isn't particularly helpful. So this is a problem that we identified, and we thought about how can we fix this? How can we resolve this? Well, and the approach that we're taking is to say, let's try and generate operators that don't break the solution, the configuration when they make a change. Okay, and so this is about producing these kind of operators that I've just talked about earlier on that are consistency preserving or sustaining rather. So if we give them a valid configuration, they will make some change, but they will also make the other changes that are required to make sure that we still have a consistent configuration. Now, this is interesting because it means we get rid of this stat solver repair step that kind of is agnostic to how we got there, and might just undo all the changes that we wanted to make. But instead, we can tie a repair to the change, and we can make sure that the repair doesn't undo the change that we were interested in. It was also interesting because we can essentially be sure that at any point in the search, all the solutions in our population will be valid configurations. And so we don't waste time on exploring invalid configurations. But of course, it brings that problem of how do we create these operators? And that's where the feature activation diagrams come in that I will talk about in a moment, because they address this recursive repair problem. So let me first, perhaps briefly, I should perhaps mention these principles here on the right. So these are essentially how we think about repair, okay? So they're basically saying, well, they're basically active variants of the constraints that we saw before, okay? So we've got this act-man thing here, which is saying, if the change that we're introducing is to activate feature F, then this act-man principle says we then also have to activate all mandatory children. And that's, as I said, that's an active variant of the CMAND constraint, right? Which was about if a feature is activated, all of its mandatory children will also be activated. Otherwise, it's not a valid configuration. And here we're basically saying, well, if the change that we're making is that we're activating this particular feature, then we also have to activate all of its mandatory children, and so on for all of these other ones. So these are all activated variants, and we have principles for activating a feature, but equally we have principles for deactivating a feature, right? Because we want to be able to do either. So here we have a variant that says if we deactivate feature F, then if this feature had some active children, they also need to be deactivated, and that's because we have this CPAR constraint that says if a feature is active, its parent needs to be active. Now, if we've just deactivated that parent, then one way of making sure that CPAR still holds is by deactivating all of the children of that parent. Okay. But you can see that immediately leads to a recursive problem, right? Because we're solving the problem with activating one feature by activating other features, and now we need to apply the principles there again, and suddenly we are in trouble. So let's just look at some examples, and this will show how we encode these operators as graph transformation rules. And you'll look at this initially and you go, they're a bit simple for graph transformation rules, and you'd be right. But in a moment, I'll explain why we went with graph transformation rules initially. This is a very simple feature model that people tend to use when they start out and doing something new in software product lines. It's this mobile media case study. And so let's look, for example, at the rule for activating this SMS transfer feature. Right? So what does it have to do? Well, in the first instance, it's got to activate SMS transfer. And the way we've encoded that is we've modeled configurations as sets of objects with one object for each feature, and they have this active attribute, which can be either false or true. And so to activate SMS transfer, we're going to say it's It was false before we applied the rule, and we're going to set it to true. But now we've got to do all the repair. Well, what does SMS transfer require us to do? We don't have to worry about media management because this is a mandatory feature inside mobile media, and this always is active, so therefore this is always active. But what we do have to worry about is that there are these two mandatory children, receive photo and send photo, and they need to be activated as well. So we say that here. And in fact, you'll notice we say they'll be activated. We don't say they'll be activated if they weren't activated before, because we want to be able to apply this rule whether or not receive photo and send photo have been active before. Okay. Equally, the other thing we have to do is we've got to recognize there's this requires rule here that says when you activate, when SMS transfer is active, copy media also has to be active. Well, so therefore we generate this additional, we have this additional bit in here that says we also make sure that copy media is active. And again, apologies, I'm coming to the end of a cold, and sometimes when I speak for too long, it makes me cough. And then again, we don't check whether copy media was active or not when we set out. So this is really simple. Let's look at a slightly more complicated example. Let's move this to the side a little bit and look at just the right-hand side of our mobile media example here with the screen size thing here. And let's look at the rule for deactivating screen 3. Okay. Now, if we deactivate screen 3, there's a few things we can do. We could try deactivating screen size, but that doesn't work because screen size is in fact a mandatory child of mobile media, and so it's always active. So that bit we can forget about. So the only way of fixing the configuration then is to say, well, here we've got an XOR thing, so we've got to either now activate screen 1 or screen 2. Okay, and so that's what we're modeling, but what we don't want to write down all of the different options as separate rules, separate operators. We want to be compact because there could be quite a lot of options here. And so for this, we use this idea of variability-based rules that I think Daniel wrote up a few years ago in the context of Henshin. And these are rules that come themselves with a little feature model inside. And then each of the things that are inside of the rule has a little presence condition attached that relates to this feature model, right? And so it's basically we select certain features here that then tells us which parts of this rule are actually going to be executed. Okay, so we're going to say, well, always, so as the root of this feature model, we're going to change the activation of screen 3 from true to false, because that's the thing that we're interested in. That's the thing that we want to make happen. But then it actually turns out we have these two options, right? We can do either screen 1 or screen 3. Well, if we're choosing screen 1, then we're going to make sure that screen 1 is true and screen 2 is false. Because then we know we have a consistent configuration again. Or we choose to make screen 2 true, activate screen 2, and ensure that screen 1 is also deactivated. And again, then we have a consistent configuration. And that means, in this case, we can instantiate two types of rules here. If we follow the feature model, we can namely these two down here, right? So we have the one where we choose to activate screen 1, and we have the one where we choose to activate screen 2. Those are the two options that we have. And this is kind of what I think also drew us into using graph transformations here, because it gives us this easy way of capturing all of the different possibilities of repair without having to spell out each path individually. We can sort of reuse this, and so these only grow in the number of possible features, and then have potentially fairly complicated constraints here that govern presence conditions, and we'll get to those in a moment. But it's as an encoding mechanism, it works really well. Now, they're still, in terms of graph transformation executions themselves, they're not particularly complicated. And so in the tool, we actually use a specialized version of the Henshin engine that recognizes that these graph transformations don't really do a lot, and that also encode the graph transformations in a more simplified fashion, but also execute them in a slightly simpler way so that they can run a little bit more efficiently. But the principle still holds. So let's walk through this and let's try and think about how we generate these pieces, just to get a sense for the complexity involved, right? So let's look at this very synthetic feature model here. And let's assume we want to produce the operator for deactivating F1 here. Okay, note that F1 has an OR group underneath it. So if F1 is active, either F2 or F3 needs to be active, but also they're the children. So if we deactivate it, they need to be deactivated. But also notice there's something about F1 requiring F4, and there's something here about F3 excluding F5. So if F5 is activated, then F3 needs to be deactivated, and the other way around. And so there's some interesting stuff going on, right? So let's step through this. What are the consequences of deactivating F1? Well, the first consequence is we need to deactivate F2 and F3, and that's by this D-child principle. So the labels that I'm putting on here, they are just the names of those principles that I showed you earlier. Okay, now, let's look at this further. So if we've done F1, deactivated F1, and we deactivated F2, what's the consequence of that? Well, F2 sits in this OR group, right? So deactivating F2 means we've got to either deactivate F1 or we've got to activate F3, right? So we're just here. These are the options that we have. And similarly for F3, if we're deactivating F3, then we've got to either deactivate F1 or we've got to activate F2. We've now got to think about what are we going to do here, right? So what are we going to do if we activate F2 or if we activate F3? What's the consequence of that? Well, if we activate F2, then we've got to activate F1. And if we activate F3, we've got to activate F1. And if we activate F1, then, well, we've got to choose one of the children to activate. But also, if we're activating F1, because we've got this requires thing here, we've also got to activate F4. And if we're activating F4, well, then we've got to do stuff about these guys here. And so it goes on, right? And so you can see quite quickly that this sort of explodes quite quickly, that the kind of consequences become quite big. Now, actually, I've shown you here already the beginnings of an activation diagram rather than showing you the individual paths individually. Okay, so every traversal through this, every traversal path here becomes a sequence of consequences, right? So if you unfold this quite quickly, you'll see that there's quite a lot of potential consequences. But what we're doing is we're not, when we're generating this, at no point in time are we ever generating all of those potential paths. What the activation diagrams allow us to do is to always reduce the problem to something that can be done linearly. And in particular, using this sort of depth-first search approach, essentially. So let's unfold the whole thing. So this is for this thing. This is the full activation diagram. Okay. And the important thing is the way we construct this is we go through all of the features in this feature diagram here, and for each we have an activation and a deactivation option, and then from that we do the process that I just talked you through, sort of going one step forward, one step forward, one step forward, and we add the consequences to the diagram. But crucially, we only we add all the possible consequences only looking at the current decision, right? So when we think about F1 minus, we only think about, okay, if we're deactivating F1, regardless of what's happened before, what are the direct consequences of that? Well, it's only these two. Similarly, if we're deactivating F2, what are the direct consequences of that? Well, it's this one. Oh, well, this one we've already explored. We already have all the consequences of that in our graph. Or this one. Oh, this one we haven't explored yet. So we now need to add the direct consequences of activating F3 to our diagram. Well, there's this one, and in fact, it turns out there's this other one because there's this exclusion relationship here, right? And by only looking at the next step, at the local direct consequences, that allows us to do the depth, to reduce the construction of this diagram to effectively a depth-first search problem. rather than something that forces us to enumerate all the possible paths, because we're basically stopping every time we find a particular feature decision in the diagram already. We say, well, all the consequences of that decision have already been explored. They're already in the diagram because by virtue of this being in the diagram already. So we don't have to carry on. We don't have to unfold all of the options here anymore. We can step back. And that's essentially what a depth first, that's the same thing as what a depth first search does, right? So it basically goes, if we've seen this node before, we don't have to worry about it. And then once we have this diagram, it turns out we can just do another depth first search over it to read off the VB rule encoding for a particular operator. So if we have this diagram and we want to read off the F1 minus thing, we do a depth first search starting at F1 minus, and everything we can find from there potentially goes into the rule. But it allows us to read off the feature model and the presence conditions as well. And so here's a diagram that tries and shows what that is. I've sort of simplified the activation diagram a little bit here. That's the activation diagram that we're looking at. So it's a much smaller, much simpler case. And on the right-hand side, you see the rule that would result from reading off for the deactivation of F1. Okay, and so there's some color coding going on here. And the first hand, you see these little annotations here, root 01, 021, 031, etc. And they relate to the features in this feature model that we create for the rule. And then you see these sort of paths here, the purple thing and the yellow thing, which might be a little difficult to see. And again, they relate to the colors of the constraints over here. And then you'll see these presence conditions and these constraints. They are also, again, color coded to each other. And let me talk you through each one of those. Okay, so for now, you'll have to trust me that we can do this with a depth first search, because I don't have the time to talk you through the algorithm. The details of that are in the paper that I've referenced earlier on the slides. But effectively, what it does is it creates a root feature, and then for every OR node in our activation diagram, it creates an initially optional sub-feature in that feature model. And then each of those OR nodes is an XOR group of sub-features, one for each edge that comes out of that OR node. So some of those OR nodes might have more than 2 edges. And then there might be more than 2 sub-features here. But in this example, it so happens that every one of the OR nodes has exactly 2 edges going out of it. And you see I've labeled them basically going, the first number is the number that indexes the OR node, and the second number then just gives a unique index to the branch, right? And so we have that. And now that in itself just encodes the one step next consequence bit. What we're going to do next is we're going to build something that allows us to transitively encode the paths. And that the way we do this is that we say, well, if we're on this path here, if we've made that choice here, or we have made the choice to activate root, or we've made the choice to activate this one, right? They all come to the same place in somewhere. What are the next OR nodes that we are coming across, and therefore where we need to activate the corresponding features? So if we're coming from somewhere here, we will next come to both OR 2 and OR 3. Okay, and so then we write a constraint that says, well, if we've activated root or 021 or 031, then we have to activate OR 2 and OR 3. Note here initially they're just optional features, so we don't have to activate them. But we're saying actually, it turns out that if you've activated one of these, then you've got to activate these 2 guys. And then the feature model rules take over again, right? To say if you activate an XOR group, you've got to activate exactly one of its children. And then from there, there's another constraint here that says, well, if you've activated 022, well, it happens to be in here, then you've got to also activate OR1. And so that's how we encode that sort of transitive next step thing in those constraints without, again, ever having to spell out all the possible paths. You will notice, however, of course, that we have some weird stuff going on here, where the activation diagram, that the stuff that we can reach from F1 minus includes weird stuff like F1 plus, right? So somewhere in here, in this rule at the moment, we're saying deactivate F1, and then we're saying activate F1. And clearly, both of them can't be true at the same time. So we're going to check what the presence conditions for these two things are. This is this and this. So again, sorry, where do the presence conditions come from, I should perhaps say. Well, they again come from reading off these paths, right? So F1 minus is present if we come in via the root path, or we come around this edge, which is the 031 edge, or we come around this edge, which is the 021 edge. Well, so we have an OR disjunction of those. And F1 minus is actually if we come down 032 or 022 or 012 and then down here, or 011 and then down here. And so we get that sort of disjunction. And what we're then going to say is, well, the two of them can't be happening at the same time. So we're going to take this presence condition and this one, and we're going to say they're mutually exclusive. And similarly for these two presence conditions here, and for these two presence conditions here. And so that then guarantees that when we instantiate this VB rule, we only get one of the two options in any case. And because this is root, it also guarantees that this one will in fact always be active, which means that this one will never be active. So we then do an additional cleanup step that sort of checks if there are any features in here that are dead, any things or any presence conditions that can never be valid, so that we can remove those things and compact our rules a little bit. Now, this is integrated in the tool. The nice thing is, in the Acapulco tool, we take a feature model, we can run this prepare step, which generates these graph transformation rules. It also potentially generates a variant of the feature model. For example, if there are cross-tree constraints that we can't handle directly, then it might apply a transformation of the feature model to produce a variant that we can handle. And then we can use these again and again to run searches and run optimizations with different objective functions, different parameters for the search, and so on and so forth, and get a set of configurations and their relevant objective functions. And again, Javi built this out into sort of a nice set of Eclipse plugins that you can just install on top of Feature ID and have a play with. And there's a tool demo that Javi gave at FPLC that you can look at. And then this then actually beats the state of the art, right? So the typical tools, the sort of Modagami and Satibia are sort of typical optimal feature configuration tools. And we ran comparison experiments with all of these feature models. So these are sort of typical feature models used to benchmark these kind of things. So you can get a sense for the size, right? So the number of configurations is good fun, including things like Linux. And there's an automotive one which is painfully large. This is the time the prepare step takes. Now, in some cases, it says 10 minutes here. That's basically just because we said, yeah, we're going to time bound it at 10 minutes. We don't want to wait for too long. So in those cases, it might not actually have generated all the operators because it didn't get through them all, because there's just too many options, or in this case, because they get a bit complicated, and so it takes a little longer. But for most of the time, you see that, even for some of these really large ones, it actually produces the full set of operators in fairly reasonable time. And then if we run this, here are some examples of the sort of typical kinds of results we see. So at the top, the diagrams are labeled hypervolume. So this is an indication of how good the solutions are that we find compared to the solutions, how optimal they are compared to the solutions that other tools find. The blue line is our tool, Acapulco. The green line is Modagami, and the red line is Satibia. It turns out that Modagami doesn't manage to handle the Linux cases, but that's fair enough because it is built to be run on mobile devices. But you can see that we are always at least as good as, but in most typically for the larger ones, then typically better than the existing state of the art. And this is execution time. So this is execution time just for the search. It's not execution time for the including the generation of the operators. And again, so here you want to see, you want to be the lowest line ideally. This is indexed over evolutions, right? In each case, so we give you an indication of how this develops over time. So you expect the lines to go up, but you can see that again, in all these cases, we're better than faster than the state of the art for research. The tool is, as I said, available as a set of plugins for Eclipse, and there's also a demo video, and I think the video is now also linked from the GitHub page of the tool as well. So what have I talked about? And then I want to bring it back a little bit to why is this SPL stuff relevant for graph transformations, right? I talked about consistency as a graduated property in the graph context, and I've talked about how it can be quite difficult to generate these consistency sustaining rules because of the fact that we have potentially the need for recursive repair, and therefore the potential for exponential explosion of these the set of rules, of the set of repair paths. We've looked at this SPL configuration as a case study where we see all of these problems, and we have a simple encoding of operators as graph transformations. And we looked at how the idea of an activation diagram allows us to consistently and the use of variability-based rules allows us to consistently avoid having to explicitly enumerate all of these paths. And therefore, that's our way of beating the exponential explosion by saying, oh, well, we're not going to actually instantiate all of those. And we do that by keeping our decision-making local and only ever looking at the direct consequences of an individual step, but coding that into a graph that then goes and has, again, the direct consequences of the next step without worrying about how we got there. So that graph might have lots of loops and things like that, but that's fine because we can, as we encode that in the VB rule, that just then becomes a longer disjunction in presence conditions, which which sort of the instantiation mechanism for VB rules is quite happy to handle quite efficiently. And it works. It generates these operators fairly efficiently. And the operators themselves are then better than the state of the art at finding more optimal configurations faster. And I said that it's available as a tool, freely available, open source, for you to check out. Where do we want to go next? I think Jens is on the call here as well. Jens Kosiol has been with me, spent some time with me over the last few months, trying to generalize these ideas of these activation diagrams away from the feature configuration case to more general graph constraints. Now there's a long road still to go. There's some very exciting stuff that's come out of this, which I can't quite talk about yet because it's not published and it's not quite wrapped up yet. And it turned out to be a little bit more complicated than we perhaps optimistically assumed initially. But there's some really exciting stuff I think that we can do there initially for a specific subset of transformations again, but within that subset then for arbitrary graph constraints, which is quite exciting. And that's sort of the next step for this work, where I think it then, apologies, perhaps links back again more to the world of GReTA, etc. And that's me done. Thank you for your attention. And if you've got any questions for the owl, then please ask them now. Apologies.
Excellent. Thank you very much for the nice talk, Steffen. And yeah, good that you made it through it despite the slight remnants of a code. So let me just check the chat. No, okay. So I had a question. I'm trying to understand essentially what is the underlying formalism you're dealing with here in more general terms, because the configurations, one way of describing them, I mean, you can represent them as bit vectors, as you said, but the bit vectors are really solutions to propositional logic formulas that express the constraints in the diagrams. Right. So I'm and then obviously you have rewriting on those, basically rewriting on sets of Boolean variables.
Yeah.
So if you just look at that, just rewriting on sets of Boolean variables, you would have basically a simple form of Petri nets, so event condition nets, as if I am correct. Andrea can correct me if that's wrong, but I think that's basically what it is. So just the rewriting part, so adding features and removing features would basically be a Petri net with basically a bound of 1 token per place. Okay. But then obviously the Petri nets don't usually have constraints over markings. So you're looking at basically at the Petri net, a safe Petri net, one safe Petri net, with constraints over the markings. So basically Boolean constraints over the markings. I'm just trying to understand. So first of all, the question is if that is correct, and I guess the question I'm asking myself, I'm not expecting you to answer that necessarily, but
it's an interesting question. So I haven't linked this to Petri nets at all so far. So so I don't know that I have an authoritative answer of any form to this question. It's an interesting way of thinking about it, but I hadn't linked it at all to Petri nets so far. Yeah. I guess the activation diagrams are a little bit like Petri nets, right? In that they have this sort of consequence flow of, if you make this change, well, then you've got to do this next thing as well, and if you've done that, well, then you've kind of got to have that next flow. So that's a way of thinking about them, perhaps. But again, I would need, I think, a bit more time to really think this through carefully. Could you
show the activation diagram once more?
I can try. Let me see whether I
wasn't actually thinking of the activation diagram as a Petri net, but it's basically a set of rules that rewrite Boolean variables. Basically, is effectively a one safe Petri net. So that's basically your set of rules is the Petri net, not so much the activation diagram. But okay. There's something similar in that activation diagram.
Okay, so so again, I would have to think about this more. So that it's not sort of a way in which I have thought about this so far.
Yeah.
But I'd certainly be interested in.
Yeah. I guess maybe the question. I mean, one question is that true or not? The other question is it helpful?
Well, it might be helpful the other way around, right? It might be helpful potentially. It might be helpful. It might be helpful in that there might be theory in the Petri net world that we could apply here, which I don't know at this point. But it might also be helpful the other way around, in that if it is true, then it may make this approach applicable to problems in the Petri net world. But again, I would have to think about this.
What I haven't come across, so that was the second part of the question, really. I'm not aware of a Petri net formalism that has Boolean constraints on the markings. So typically, as far as I know, a Petri net is basically a rewriting system on sets of tokens.
Yeah.
So if you do if you rewrite sets of tokens, or a graph rewriting system that just rewrites nodes, effectively you can think of this as a Petri net. Okay, and in your case it's even slightly simpler, because it's really just switching on and off existing nodes. So that's why I say it's a one safe Petri net, so basically a condition event system. But what Petri nets normally don't have are constraints on the markings.
Yeah, because that becomes complicated to
and that may just be either.
Yeah, and that's what we have here, right? So because we have to be that's really what the activation diagram is about.
Yeah.
And I think just on that link, Arthur asks whether activation diagrams are supposed to be human readable. The answer is emphatically no. They're very much an internal data structure. This is, I mean, you see, this is a very small feature model, and you already see how painful the activation diagram becomes. For realistic feature models, you don't want to look at the. I mean, I had to do it as part of debugging the implementation. It's really, I built some graph transformations on top of my visualizations to even try and make sense of things there, and it becomes painful really quickly. So we did some complexity analysis, and the growth of these beasts is bounded, or is bounded reasonably. It's a good way away from linear, but it's at least not exponential. And it's very polynomial, in fact. But they still do grow, and in particular, the number of edges and number of nodes is linear in the number of features, because it's basically for every feature you create 2 nodes. But the number of edges grows polynomially, unfortunately, which because you get because in particular it grows whenever you have one of these groups. Yeah, then you immediately get all the, well, if you select this one, you've got to deselect the others kind of things, and that one for each member of the group, and that kind of messes you about a fair bit.
Thank you. Regarding the other question on the on why they avoid the enumeration of all possible repairs, is that because of the cycles primarily?
Well, no, it's because and I've realized when I put together the presentation already, I kind of realized that that's probably going to not come across so well. And I should probably have done an example of enumerating things more explicitly, because at every step here, we're only looking at the immediate consequences, right? And so when we're generating this diagram, we're basically, what we're doing is we're going through all the non-core features, so all the features that we know aren't on by default, and that's it. So finding core features is a solved problem in the feature configuration world. So we know that there are only certain features within here that actually can be activated or deactivated. We go through all of those, and for each one of them, we add an activation decision and a deactivation decision to the feature diagram. And every time we add a decision to the diagram, the first thing we do is we go, is it already in the diagram? And if it's already in the diagram, we go, we're done. Because when we add a new decision into the diagram, we will also add all of its immediate consequences to the diagram, and therefore we know we're done. Okay? If the decision is not yet in the diagram, then we add that decision to the diagram, and then we generate all the immediate consequences by following the various principles that we've defined. And those create new feature decisions, and we add all of those to the diagram. And we do the same thing again there, right? For each one of them, when we add it, we go, is it already in the diagram? Ah, good, thank you, done. Is it not in the diagram? Well, then we've got to explore that next step. But that means every edge in this diagram here, when we're generating the diagram, every edge we will only touch exactly once. Namely, at the time when the source decision of that edge gets actually added to the diagram. And that means we avoid having to explore all the exponential mass of all the possible paths. And then similarly, so this is the first step, but then when we create the VB rules, we could have a similar problem, right? Where we go, well, now we have to explore all the paths so that we can work out everything that needs to go in the VB rule. But it turns out we don't, because we can again just do a depth first search over this diagram and keep track, as we do that, keep track of the presence conditions that we've accumulated so far And we also keep track of when we hit an OR node, we use those presence conditions to keep track of those sort of OR activation things. There's a few additional little bits and bobs that we need to generate to make sure that our VB rules don't produce more than necessary instantiations, but essentially we can again do depth first search, and that's great because depth first search obviously is linear in the number of nodes and edges in the graph, and therefore the overall complexity of this algorithm can be directly related to the size and structure of the original feature model. But I've left that stuff out of here. If all of that's in the paper or in the appendix to the paper, in the TSE paper, which is somewhere up here. Andrea, I think, has his hand up while I search for that reference in this paper down here. Sorry, Andrea.
Yes, Steffen, thanks for the very interesting talk. So when you essentially when you start explaining the problem and presenting these activation diagrams, I was thinking that you basically have an operational approach of the following kind. You think of a rule for transforming the graph or whatever it is, and then you have to make the rule more complex in order to make it constraint sustaining and so on. In the end, what you get is an operational model where each activation diagram is applied like a complex rule to the diagram. Then you can apply another one and so on. And you are ensured that you move from a configuration to one which is at least as consistent. So basically, you avoid exploring configurations which are, or you avoid reaching configurations which are bad, which are less interesting than the other one. Another approach that we followed in some work several years ago was to consider a notion of transaction. A notion of transaction in the sense of the possibility of applying a rule that in any case leaves you in a state which is not stable in a sense, and you can consider it as not visible from outside. So in a state of this kind, you are forced to apply other rules when you don't reach a state which is again stable and visible from outside. I like to say you have transactions in database queries, and you don't want to consider possible inconsistent states in the middle, but you consider only the stable state you reach. And we were modeling these in a graph transformation in a suitable way, but actually by the observation of Rykov that these are actually one-safe nets, it's possible more easier to consider what was actually the source of our contribution for transactions in graph transformation, which came from the world of Petri nets. And these are the zero-safe nets by Montanari and Bruni. In zero-safe nets, you basically have the possibility of defining, okay, I don't want to go into details, but you have a very elegant way of defining a net where certain states are not considered, are not legal markings in a sense. You are forced to move from this illegal marking by applying some rules. So this will mean that in a different approach to your problem, one could think to an activation diagram not as something that you prepare statically, in the sense you analyze all the possible illegal outcome of the application of a rule, but you could get the same effect by programming them. So you program the repairing of the graph by some basic rules, so elementary rules, and then having a way to determine that when you reach a certain configuration, okay, this is the final result of repairing the first application. Therefore, this is visible again. So this will be a more, let's say, dynamic approach to your problem rather than a static one where you design the rules since the beginning. It was just an idea. So, but in any case, the immediate feeling I had that some notion of transaction could move from the static analysis to the runtime, the handling of inconsistencies.
It's worth exploring, I think. I think it's my feeling is that you still need a mechanism for handling the potential for explosion of the number of paths there. But because you still would need to encode that in your Petri net somehow. But it's worth exploring, I think, and I think the activation diagrams would still would probably still give you that, and then you might want to look at, can I go from an activation diagram into a Petri net encoding, for example. So I will just read off a single rule. Apologies. I wouldn't read off a single rule, but read off a Petri net instead, for example. Which is essentially, which corresponds to a graph program, then I guess, rather than a single rule. So if I interpret correctly what you've said.
Yes.
The question is, I guess, so this activation diagram may be a control. Yeah, so I think, yeah, maybe so the intuition I certainly agree with. So in a sense that the activation diagram is some kind of control structure over rules, or can be used as such.
Yeah.
But the different granularity with respect to the main control structure. This is the idea, because the main one are the rules, and then for each rule you have another bookkeeping computation.
Exactly.
You can you could express this with a small program.
But so the activation diagram is I think, and I think that's kind of partly, I think, what we see as we try and generalize this a little bit with the ends as well. I think you can start to think about the activation diagram as, you could think about it as a graph program, right? That where the edges are essentially then, or rather, sorry, not the nodes are applications of rules, right? Of sort of atomic rules. In this case, it's a bit silly because the nodes are essentially switch a feature on or switch a feature off, but they could be more complicated beasts, right? If in a full graph transformation world.
Yeah. So can you show that again? I had another sort of correlation that sort of occurred to me. Sure. The diagram, the activation diagram. Yeah, that will do. So so I was thinking from a logical point of view. Okay, so if these are all Boolean variables, yeah, then F1. So let's say if F1 is a Boolean variable, then F1 minus or F1 plus, you can think of literals. Yeah. In a logical sense. So positive or negative statements of the presence of this. And then the edges here, or maybe the collection of outgoing edges from each of these nodes, basically represent some kind of clause. So of the form literal implies, and then some kind of expression that basically tells you what is fair and what is not there. So I wonder whether you're getting close to resolution algorithms here, which work on such clauses. I mean, you can normalize them into these kind of normal forms that you have, and then I mean, what is slightly funny here is that you have clauses that have where the head is a literal, which normally you wouldn't, I think. But yeah, I'm just wondering whether there's something related to resolution here because there are lots of sort of interesting algorithms for that, of course. And it also has been sort of generalized from obviously propositional logic to higher logics like first order logic and things like that.
I agree. So I think there's probably a good relationship to that. I think one of the things that I'd love to have the time to do is at some point is to understand generally how some of the stuff we do here relates to the sort of algorithms that people who build stat solvers and things like that actually use, which I know too little about to really comment on. But it seems to me that there must be, there's probably something here that we're reinventing that somebody in the stat solving community would look at and go, yeah, that's kind of what we do. That I just don't know about.
I mean, certainly on this kind of propositional level, I would expect something like that. Obviously, if you go beyond that, as I said, I mean, I don't know whether the kind of the variant of that works with more general rules comes closer to kind of the equivalent of first order logic. I cannot judge that, but anyway, so you're probably aware of that, so I'm not telling you anything new there.
So I'm aware that there's something to be explored there, but I'm not necessarily aware of the specific work and how it precisely relates. Cool. I'm afraid, slightly bad news. I managed to misplan my time a little bit, and I should be going to another call momentarily.
But
I also have to leave. Steffen, thank you very much. Even with your state,
apologies for making you listen to my coughing.
That you had to give the talk in this condition, but it was extremely interesting.
That's good. Okay, so then I suggest that we thank Steffen again and close the official part of the seminar here, and wish you all a good year and a Merry Christmas, or the other way around, depending on what you do in which order. There are people who have that in the other way around, I think. And we see you all back in January, I think, with Manfred Nagel in sort of.
Yes, so that's going to be on the 13th of January, and he'll tell us about some links he found between architecture of Gothic churches, I think, and gospel writing, and and also from my side, thanks a lot, Steffen, for the talk under these difficult circumstances, and good end to the year to everyone, and well, until next year.
Until next year. Thank you very much. Bye.